The last thing in this particular topic, we're going to talk about this idea called differentiability. We talked at the start of the topic about continuity, or curves being continuous. And you might remember the definition for a continuous curve was that if we get the limit from the positive side and it equals the limit from the negative side, then the curve's continuous. There's no break in the curve. Now that actual idea, as I mentioned, is not actually in the course. We just really need to be able to look at something and say, oh yes, it's continuous, or no, it's not. And so, we can look at our hyperbola and we can clearly just say, oh, it's not continuous at x equals 0. We don't have to use limits and what have you. Differentiabilities are similar to that, but it's where we look at the derivative. A function can only be differentiable if the curve is what we call smooth continuous. So it has to be continuous, but it also has to be smooth. So the formal definition, which we don't have to know, is this time we look at the limit of the derivative. And the derivative has to be the same when we look at it from the left-hand side and the right-hand side. Now, what does that look like as far as a picture goes? There's our absolute value curve. That is differentiable everywhere except one point. Which point do you think that might be? Yeah, over here at x equals 1. And that's all you would ever be asked to do when it comes to differentiability. It would say, at which point is it not differentiable? That's the sharp point, basically. Because if you look at the left-hand side, the slope of the curve, which in this case is a straight line, is different to if you look at it from the right-hand side. So it's not smooth continuous. It's continuous, there's no gap there, but it's not smooth. So not differentiable at x equals 1. Okay. And the formal, but as I say again, you don't need to know this. The formal definition, we would go, oh, well, if I look at the limit from the left-hand side of the slope, it's -1, but on the right-hand side, it'll be +1. They're not the same, so no good. As opposed to my parabola, that's smooth, continuous everywhere. There are no sharp points, there are no gaps. So you could substitute any x value into the derivative and come up with a slope. And so if I use x equals 1 again as the example, that one is differentiable at x equals 1 because there is only one tangent we could draw at that point. And so yes, it is differentiable. All right, enough about that. As I say, in reality, all you'd ever be asked to do, they'd probably draw a picture or they might give you an equation of a function so you draw it up for yourself and you can see for yourself, are there any discontinuities or are there any sharp points? And that's basically all we need to know. Implicit differentiation is just a really fancy title for what we looked at yesterday, rates of change, which again was a really fancy title for the chain rule. It's all the same thing. So what do we mean when we say implicit differentiation? It's again, look at that, it's the chain rule. It's the same rule yet again. Let's do an example. You see, where it has its advantages is it saves rewriting the equation. See, for this one, to find dy dx, I would have to make y the subject. So what I'm going to do instead is go, no, I'm just going to differentiate both sides with respect to x. Okay? Because essentially that's what you're doing when you differentiate it. It's an equation, and what you do to one side of the equation, you do to the other. Now, we don't normally write this line in. We're saying, I want to differentiate with respect to x. Now, the left-hand side's not an issue. I can differentiate x with respect to x. But the right-hand side, I've got a problem. How do I differentiate y squared with respect to x? And that's where the chain rule or implicit differentiation or rates of change, call it whatever you like, comes in handy. And the way to think about it is I say, well, I can't actually differentiate y squared with respect to x. But I could differentiate it with respect to y, and then I could multiply that by dy dx, and it would balance out. It'll be okay, because the dy's would cancel, and it'll be with respect to x. And so that's what we do. So I see that. I don't normally write that second line down. If I see x equals y squared, I say, all right, I'll differentiate the left-hand side with respect to x. That's 1. The right-hand side, can't differentiate y squared with respect to x, but I can with respect to y. So I'll make that 2y, but I have to multiply it by dy dx. And now I can rearrange this, and there's our derivative. It's just that instead of substituting in the x value to get the slope, I'd substitute in the y value. That's the only difference. Let's have a look at another one. So I can use the product rule. If I had some combined function like this, x squared y cubed, and I wanted to differentiate that with respect to x, I'd go, oh well, write down the first, x squared, diff the second, y cubed. Oh, can't differentiate y cubed with respect to x, but I can differentiate it with respect to y, so that'll be 3y squared, but then I'd have to multiply it by dy dx. Plus, write down the second, y cubed, diff the first, 2x. So tidying that up, that would be the derivative. 3x squared dy dx plus 2x y cubed. So if I want to find the equation of a tangent to a circle, so prior to today, I would have said, okay, got to find the derivative to get the slope of the tangents. So I'd have to rewrite x squared plus y squared equals 9 to make y the subject, but now I don't have to. So, well, x squared plus y squared is equal to 9. I'm just going to differentiate everything with respect to x. Okay, differentiate x squared with respect to x, oh, I'll get 2x. Differentiate y squared, oh, can't do it with respect to x, but I can do it with respect to y. So differentiate y squared, I get 2y, but then I've got to multiply it by dy dx. Equals, on the right-hand side, differentiate 9, well 9 is just a constant, so that becomes 0. Rearrange it, and eventually, there it is, dy dx. This time, I've got to use both the x and the y value to come up with the derivative. We want the point 1, 2 root 2. So subbing in 1 for x and 2 root 2, there's my slope, negative 1 on 2 root 2. And then it becomes exactly the same question. All right, point slope formula, y minus y1, so 2 root 2, equals the slope, minus 1 on 2 root 2, times x minus x1, well, in this case, 1. I put it in general form, I think, did I? Yes, there it is. X plus 2 root 2, y minus 9 equals 0. Now, this idea of implicit differentiation really is an extension 2 idea. They won't specifically ask you in extension 1 to differentiate something this way. However, if you did want to use it, there's no reason why you can't. Because I say, all it is, it's the same as a chain rule, it's the same as our rates of change idea, it's just another fancy word for the same thing. What it basically means is, when you make y equals the subject, you are differentiating explicitly, because you've made something the subject. Whereas here we're differentiating it implicitly, because we haven't made anything the subject of the formula, it's all mixed together. Hence the fancy name. See, you didn't think I knew English, did you? Okay, exercise 7K. As I say, it is extension 2 stuff really, but have a go at it. See what you think.